morning, everyone. My name is Quinn Armitage from Service Heat Treating, a member of the MTI Institute. I would like to welcome you all to FNA 2024 technical sessions provided by the Metal Treating Institute and the MTI Educational Foundation. Before I introduce the session, there's a few housekeeping items I'd like to take care of. First, we'd appreciate if everyone silence their phones and put them away. During this session, we'd ask that you don't take any pictures or video. The video will be taken by the MTI and provided and edited after the meeting. Lastly, there's some QR code wall clings on the walls. Instead of paper surveys, as we've done in the past, you scan the QR code, fill out the survey online. These help us improve future technical programs. Each session survey that you do fill out, you get entered to win a $100 Amazon gift card. So now for our session. We have the impact of oil quenching, a look at the carbon footprint and costs of vacuum versus atmosphere processing. Help me welcome your speaker, Mr. Brian Stern from Gasbarre Thermal Process.
Thanks, Quinn. This is the
presentation.
Oh, okay.
So it wasn't right.
Sorry about that. Well, good morning, everybody. Thanks for being here. A lot of work's gone in the background to pull together the data that we'll be going through today. So we really appreciate your time choosing to be here with us. Hope that you can take something of value away from this. We're aiming for just an increased familiarity with some of the dynamics that are at play in the background when we're comparing the atmosphere versus vacuum equipment. So we'll jump right in. They say to start a presentation talking about what you're going to go over. I wanted to start by talking about a couple of things that we're not going to go over. We're not going to talk about the backdrop of environmental policy, and that's kind of driven a lot of interest in this. We're really focused on the data from this presentation, so we're looking at data, not pictures of polar bears. I'm sure everyone has different reasons for being here, and different reasons that you might be interested in this presentation, whether it's the environmental side, the cost side, but that's going to vary for everyone in the room. We're not going to go through a detailed tutorial of how to do the calculations here for the energy consumption, the operating cost, or the carbon emissions. We'll be mostly doing a high-level overview of the results with a brief background of some of the methodologies, but if you're interested in more information on how that was done, feel free to reach out to me, talk to me after the session, find me at our booth, or just reach out after the presentation. I'll have my contact information at the end. And we're also not going to tell you what type of equipment to buy. We're in the unique position of offering both styles of equipment that we're talking about here, so we saw that as a unique opportunity to kind of give an unbiased review and analysis, provide that information. It was helpful for us just to gain a better understanding, and so we wanted to be able to share that with you. Another thing that I don't have on here, but has come up before that we won't be going through is there's a lot of other reasons to consider between these two styles of equipment, whether it's metallurgical, work environment, safety, between vacuum and combustion-fired atmosphere equipment. I'm not dismissing those. My background's in vacuum, so I'm kind of biased there too. I think vacuum offers a lot of wonderful advantages, but we're really focused on comparing them across these metrics, so looking for more of a qualitative comparison and less quantitative with some of the other things that you might consider, but just want to acknowledge that those are there, just outside the scope of what we'll be talking about. So what are we going to do? We're going to go through a case study comparison between a natural gas-fired IQ furnace and an electric vacuum oil quench, running the same workload, the same process, and we'll be going over their results for energy and utility consumption, the operating costs for that cycle for each piece of equipment, and the carbon emissions. We'll also look at just a couple variables that can kind of change those results. There's a lot of variables that can have an impact, but we'll highlight a couple, and then we'll summarize takeaways at the end. So our objective here is to equip you with information and just gain some familiarity on the data behind what's actually going on in this comparison. So we'll run through a background, going over the equipment, the workload, the process, brief overview of the calculation methodology behind it, go through the results for the energy consumption, operating cost, and carbon emissions. We'll talk about some of those key drivers and summarize the takeaways. So jumping into the furnaces, we have the atmosphere IQ on the left and the batch vacuum oil quench on the right. The objective here was to try to have as apples to apples a comparison as possible. So we wanted these furnaces to be as similar as we could feasibly make them. They both have a 36, 36, 48 work zone. The Atmosphere IQ uses indirect fired recuperated burners for its heat source, while the vacuum uses SCR fired electric heating elements. So that's one of the main key differences. Another important distinction is that the Atmosphere furnace has 12 inches of ceramic insulation, whereas the vacuum furnace just has 2 inches of graphite felt. And that's pretty typical for vacuum equipment, or to see that difference between vacuum and Atmosphere, just because the less insulation is used to preserve the quality of the atmosphere and maintain a good pump down time. But we'll see how that difference is something that'll play into the results significantly. One other difference is just the way that each furnace produces its atmosphere. The IQ on the left uses endothermic gas for its protective processing environment. This furnace was measured at 750 CFH, whereas a vacuum furnace uses pumps to remove the atmosphere, in this case a roughing pump and a booster pump. So two different methods of accomplishing the same thing, but again, one of the key distinctions that we'll see kind of show up and make a difference in the results as we look at the comparison. There's a couple other minor differences, like with the total workload capacity and the max operating temp between the two furnaces. But because we're looking at the same workload in each, operating the same thermal cycle, same temperatures, that's going to kind of come out in the wash because we're running them the same way and using the same capacity. So speaking of the workload, we'll be looking at just basic neutral hardening process. The workload will be 2,500 pounds of 4140 steel. With an hour 45-minute ramp rate, so that corresponds with about 15 degrees a minute, so a really typical ramp rate going up to 1550 and holding for 2 hours, followed by an oil quench. So we picked this cycle just to have a very clean baseline for comparison. Obviously, there could be a lot of different permutations for the thermal profile with different preheat temperatures, different soak times, ramp rates, et cetera, but we wanted to just go with something kind of middle of the road to get an idea of how they stack up. So here we have an information flow diagram breaking down just kind of the process behind this. So you can see on the left, we're feeding workload and fixturing information, so things like specific heat, the mass of the workloads, and each of the fixtures, along with the thermal cycle definition, so what we saw before with the ramp rates, holding temperatures, hold times, and operating and performance data measured from the furnaces. So things like power consumption for pumps, et cetera. We're feeding all that into a furnace model to come up with the energy and utility consumption for this particular cycle. Then once we have that energy consumption, we're taking utility prices and combining it with that to come up with the operating cost for the cycle. And on the bottom, we're taking emissions factors, adding them into the energy values that we have to come up with the equivalent carbon emissions. And I know I said we're not going to get too far into the weeds, but I did want to just go through some basic carbon accounting terminology for anyone who's not as familiar with that. Yet there's a pretty common misconception that eliminating on-site combustion and moving in the direction of electrification can just eliminate carbon emissions in general. And that might be the case if you're contracting specifically for renewable energy, but in most cases, you're required to account for all the emissions associated with your process. So that'll cover things like the direct emissions from burning fossil fuels on site, which would fall under Scope 1. It also covers any emissions generated as part of generating the electricity that you consume on site. So fossil fuel fired power plants also fall under that, and that would be under Scope 2. And it covers anything associated with the delivery of your product or products that are used in your process, which fall under Scope 3. So an example of that would be delivering finished goods or delivery of nitrogen if you have compressed gas or liquid nitrogen. So just delivery costs, and that's going to vary some depending on your location. So nice thing about that is we can take emissions factors and use them to translate those different utility consumption values directly to equivalent CO2 for a comparison. Some of those values are fairly fixed, like the amount of CO2 that's generated when you burn a fixed amount of fossil fuels in a burner. That's a pretty fixed value, but some of them will change, like I mentioned, the nitrogen. Depending on your nitrogen infrastructure, you could have, if you're delivering compressed gas versus delivering cryogenic liquid or generating on-site, depending on your storage capabilities, distance to suppliers, all those things can have an impact on what the emissions factor would be for that. So there's some variation there, and very importantly to what we're looking at, the electric emission factors can change as well, depending on the sources for generation for that region of the grid. But those emissions factors and utility prices are published by the EIA and the EPA, which gives us a nice baseline to reference published data for what those can end up being. So we'll dive right into the results. Simple slide, a lot of work going in behind it. But this is kind of an overview, but there's a couple kind of important observations that we'll unpack just right out the gate. So the first thing that we see is that the atmosphere IQ is consuming about 2,400 MBTU of energy for the cycle, whereas the vacuum furnace is right around 1,500. So that's about a 60% increase in energy consumption for the IQ furnace, which is big. And the next couple slides will dive into more of why that is. But despite consuming substantially less energy, the vacuum furnace at $35 a cycle is around twice as expensive to operate as the IQ at $17. So that's primarily due to the fact that electricity is just a more expensive energy source for firing the furnace. So despite that difference in consumption, the vacuum furnace ends up being more expensive to operate. And there's a similar story with emissions, where the emissions factors for electricity tend to be higher as a result of all the efficiencies along the supply chain of delivering that, because again, unless it's renewable to start with, you're generating it, transmitting it, and for thermal processes, in the end, that tends to have a higher carbon impact than just burning those fossil fuels directly on site. So I threw this slide in just to give an idea of all the pieces that are coming into these models. It's a little bit overwhelming with all the lines there. So what we wanted to do was kind of distill this down, make it a little bit easier to process, simplify the data. So we took different things and distilled them down into categories, so you can see things like the thermal storage for the baskets, grid, work, and the furnace are all combined into just one piece for the total thermal storage, just to simplify what we're looking at. So this particular pie chart is for the energy on the IQ furnace, but we did the same thing with each of the charts. So just so we know what we're looking at here. So starting off with energy, one of the first things to just point out is with the thermal storage losses, those are essentially equivalent for each furnace because we're running the same workload, same material, same mass. They show up as different percentages just because the totals for each furnace are different, with that atmosphere IQ being higher. But those numbers are essentially equivalent. And then moving on to the thermal insulation losses, which if you're like me, that's one of the first things you think of when it comes to energy consumption in thermal processing equipment. That makes up 30% of the vacuum, and it's only 5% of the IQ, which isn't terribly unexpected because if you'll recall, that IQ furnace has significantly more insulation, but it really shows up here in the thermal losses and how much more efficient the IQ is. But that kind of begs the question, if the thermal storage is essentially the same between the two pieces of equipment, And the IQ furnace is a lot more efficient as far as thermal losses. Then why is the IQ consuming more energy? And this was one of the more eye-opening pieces for me going through this, was just to see that the endothermic gas is such a huge contributor to the IQ furnace. So the gas flow itself for conversion is 28%, but that doesn't even account for the generator burner, the controls for it, and the electric auxiliary. So it ends up being about 42% of the energy consumption from the IQ is coming from the atmosphere generation. Whereas with the vacuum furnace, with those two pumps running, we're looking at about 11% of the total consumption. So even though the vacuum is not more thermally efficient, it's a lot more efficient at generating a protective atmosphere. So with operating cost, it's a similar breakdown, because if you'll recall from that information flow diagram, it's based on energy and just the utility costs are applied. So we have the introduction of a couple other things that weren't included in energy consumption, like nitrogen gas usage. But the big thing here is that anything that's electric basically gets inflated for both pieces of equipment. And you can see that really clearly with the furnace auxiliaries on the IQ, which only made up 9% of the energy consumption contribution, but make up a full 20% of the cost. And the same is true with the vacuum furnace, where you really see it blow up with all the thermal components, losses, storage, and ultimately landing the vacuum furnace at that higher price point to operate. And the carbon emissions is a very similar breakdown, same story. It's not quite as extreme because the relative emissions factor of electric to gas is not as dramatic as the price point between those two. But we have a similar breakdown with, again, the vacuum furnace generating slightly more carbon emissions, but not nearly as extreme as the price difference. So this is about 25% more carbon generated from this cycle in the vacuum furnace. So I know we kind of just mentioned that there's a lot of variables that go into this that can change it, and we're not going to go through this whole slide. But it's just to illustrate all the things that are in the background that could change the outcome that we're looking at and the results that we just looked at. So you can think things like if we had a longer hold time, if we changed the mass of the work that we're processing, if we sized our pumps a little bit differently or had a different endothermic gas flow, all those things are going to change the outcome. So the question was, which ones matter most? What have the biggest impact, and consequently, which ones should we be paying attention to as we're looking at purchase decisions or designing equipment? What matters for changing these results? And that kind of, with the model at our disposal, we could play around and kind of do a sensitivity analysis on where we could poke this thing that it would change the most. And that distilled down to these 7. I don't have time to go through all of these, so we're going to cherry pick a little bit and look at number 2, the electric element conversion, number 6, the geographic location, and number 7, the furnace configuration. So all these are available, and we do have a full-length webinar and slideshow. So if you're interested in that, just come talk to us and we can hook you up with that information. But we'll just jump through a couple right now. So with the electric element conversion, this is looking at the scenario of what if we took that gas-fired IQ and just put electric elements in it, which is a pretty popular target for electrification, just a green initiative. Let's put electric heating elements in. And we do see a drop in the energy consumption. It goes down by about 9% for that furnace. And that's primarily coming from the fact that we've eliminated the exhaust from the burner and that inefficiency that isn't present with electric equipment. But again, because of the higher cost of that electricity, the operating cost goes up by over 50%. And most importantly, the emissions goes up by 20%. So if this was something that was being done to try to reduce the carbon footprint for that equipment by applying electrification, that would actually have a counterproductive result in this case. But it depends a lot, as we mentioned. Some of those things can change, like the electric emissions factors. which is why I wanted to talk about location, which is a super important point. The numbers that we went through are just US averages for the utility prices and the emissions factors, but those can change dramatically depending on where you're located. So we're going to take the case study and we're going to bounce it around to a few different states and just pay attention to how the results change, the relative results. And keep in mind, the energy is not going to be changing. The furnace is going to consume the same amount of energy no matter where it is. But the operating costs and the carbon emissions will change based on those varying utility prices and emissions factors. So pay attention to the green bars and the blue bars, and I'll jump through a few different states here. So we've got West Virginia, Michigan, Texas, California, Delaware, Oklahoma, and Vermont. So you can see even from that last one just how dramatic that is, that just by changing the location, it totally changes the outcome of which furnace is preferable, at least from an emissions standpoint. And there were some within there that the cost changed dramatically as well. And just to comment on the states we've selected, definitely acknowledging that Vermont is not known as an industrial hub for heat treating. But the states that were selected were really to show some of the more dramatic swings, so showing Pennsylvania next to Ohio. A lot of the states are more, or they're closer to the US average. I can say from going through all of them, there were about 10 states in which the electrical generation makeup was such that it favored the electric vacuum furnace for emissions. But the point being that location and paying attention to your specific geographic context is really critical for making any decisions, because if you don't bear that in mind and just go with a general guidance like electrify this or go with this strategy, depending on the context, it may not have the effect that you're looking for. And then one other one that we wanted to go through here was equipment configuration. And this is one that I wanted to talk about because I think it's very often overlooked. The furnaces that we were comparing here are the two on the left, so the Atmosphere IQ and the batch vacuum. And that's an intuitive comparison because they're both batch furnaces. So it seems like a great head-to-head stack up. But the IQ furnace that we're looking at has the capability of loading a new workload over the previous quenching load. So we call it loading over oil. So consequently, and the vacuum furnace also has additional time required for pumping down that's added to the cycle. So we see the index rate, so the rate that work is changing positions in the furnace, go up by 50% to go to that batch vacuum furnace. And consequently, the utilization and the throughput, the amount of work that we're actually able to get through that furnace, drops by 33%. So it's not really a great apples to apples comparison for an application that requires the same throughput. And a better configuration as far as throughput to compare would be that same vacuum furnace, but in a continuous configuration with a single heat chamber. So that's shown here. That's very small cost increase on the capital side because we're just adding another door. We do need space to unload it. But if you were to go to that configuration, then the throughput is the same as the Atmosphere furnace that we were looking at. And we see the energy consumption drop. The cost does go up a little bit. And I was curious why, because that result fell out of these models. And diving into it is because there was an additional nitrogen backfill required for the transfer. So it does increase the cost over the furnace we looked at just a little bit, but the emissions go down as well. But if we were to add another heat chamber to it, then we would see the index rate decrease by 44%. So the throughput utilization go up by 66%. So you're getting way more through. And your energy consumption is dropping by 16%. The cost is dropping 3%, not a ton. And the emissions is dropping as well. So then you start to really see how that equipment configuration and what you're targeting as far as throughput can have a pretty massive impact as well. So again, it depends what you're comparing, and the comparison, is it really apples to apples? What application are we looking at? What throughput matters? But you can see that there's a lot of advantages that come into play with multi-positions like that. So going into our takeaways from this, I know that's kind of a fire hose of information, a lot we went over, but we'll distill it down. So gas-fired atmosphere furnaces will typically consume more energy. That's generally true with the asterisk caveat. It depends a little bit on what atmosphere you're using. But in general, they're going to consume more energy. Electrification does not always reduce cost and emissions, so that's a big thing to keep in mind. It's really important where your electricity is coming from, if that's the target of what you're doing or why you're choosing electric-fired equipment. And the growth in the renewable sector, which in the longer version of this, I did go over a little bit how the renewable contribution to energy generation is increasing, where it's kind of expected to be in the coming years. As that increases, emissions factors for electricity will continue to drop, and that will increasingly shift toward favoring electrification. But as we saw, some of the other variables might be more important, like where you're located. So some of the key drivers that impact the results that we went over are the equipment design and operation, what configuration you're looking at, what throughput you have, your utility infrastructure, how you're sourcing your gases, where you're getting your water from, and location is huge. You really can't make well-informed decisions without factoring in the specific geographic context that you're making them in. And then finally, multi-chamber and continuous furnace configurations can offer benefits that can tip the scale in favor of electrification. We're seeing here that even with those US average numbers, that at the baseline where the vacuum was not favored initially from an emission standpoint, changing that configuration allowed improvements across all three of the categories and metrics that we're looking at. So work with your OEMs to figure out what your best solution is. They should be able to help you walk through and figure out what's best for your context based on whatever your supplier infrastructure is and what you're trying to do. So there we've got some references, and thank you.
So does anyone have any questions for Brian?
So definitely appreciate choosing that neutral hardening process for like doing apples to apples comparison on these. I was wondering though if you might have a good feel on how they might compare when you start looking at something like gas carburizing versus low pressure carburizing, like the generation and transport of your natural gas versus acetylene, and then also taking into consideration things like shorter cycle time since you can carburize at a higher temperature in your vacuum furnaces.
I don't. We've talked about looking at it. We'd like to get a feel for, especially with carburizing, how does that stack up based on the changes with cycle time, like you mentioned, as well as just the gas supply infrastructure. So hopefully coming.
That's a great question. I had the same one, but I was also wondering about the Vermont energy costs and the emissions energy. I would expect it to be the opposite.
So the cost flips, I haven't dived into exactly what's driving those low emissions factors for electricity in Vermont, but I believe it's because they've really focused on a lot of renewable generation sources. So it's California is another state that's similar. Just so you could probably tell by the color of a state on a political map where it's going to fall with the emissions factors.
The emissions is would be the same generation of energy as whatever energy they have available for the state.
Yeah. So there's it's a ways back in there, but you can look at the presentation, the slide that had the different scopes on it. There's a map that's published for the different electrical grid supply regions, and so it's usually not by state. It's actually those regions are not necessarily bounded by state lines, and that's what those emissions factors are published for. So when we're looking at a state average, it's actually usually a combination of a couple different electrical grids that overlap in that state.
Brian, first of all, very well done, thank you.
Thank you.
So in your presentation, you looked at multi-chamber vacuum furnaces, and obviously, there's an advantage to be had there in terms of energy utilization and then subsequently emissions. Had you given any consideration to utilizing that same thought process in multi-chamber, continuous atmosphere furnaces?
I've thought about the comparison if we were to branch out. I think a lot of this,
There's so many iterations.
yeah, a lot of the same benefits I think would come from there. So just looking at making sure that, this is a bit behind the curtain. I didn't discover that difference in the throughput until later on in the process of putting this together. So my attempt at the apples to apples comparison kind of blew up when I realized that. So it taught me the importance of the configuration, and that's really what I was looking to illustrate, is that to do an apples to apples, whatever you're looking at, whether it's continuous atmosphere or continuous vacuum, should be comparable for an application if the throughput is something that you're targeting a fixed value. Any other questions?
All right, let's thank Brian again.
Thank you, Dennis.